Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the inflating process. In addition to a large number of stable fluids in engineering, there are also some unsteady fluids. The inflating process is a typical unstable fluid. When inflating, in addition to the flow rate changes with time, the state of the gas in the container also changes with time. Generally, it can be considered that at any instant, the state of the gas in the entire container is approximately uniform. Pressure and temperature are consistent. When inflating a container from a gas source, the gas source usually has stable properties. Take the gas in the container as a thermodynamic system, and its volume V does not change. The temperature of the gas in the container before inflating is T1, the pressure is P1, and the mass is M1. After inflating, then, the pressure rises to P2, the temperature is T2, and the mass is M2. According to the basic expression of the first law, that is, equation 2,4, we have the following expressions for the inflating process. We then have the general energy equation of the inflating process. This is equation 899. There are two typical situations when inflating. The first one is the fast inflating. The inflating process is complete in a short period of time, or the container has good thermal insulation, so that the inflating process can be considered to be performed under conditions that are basically insulated from the surroundings. The second one is the slow inflating. The inflating process is completed in a long time, or the container and the surroundings have good heat transfer conditions, so that the inflating process is basically carried out at a fixed temperature. Let's firstly talk about the fast inflating or the adiabatic inflating. For adiabatic inflating, simplifying equation 899, we have this energy equation. This shows that the thermodynamic energy of the gas in the container after adiabatic inflating is equal to the sum of the thermodynamic energy of the original gas in the container and the enthalpy of the filled gas. If the gas in the container and the inflating gas are the same gas with the same specific heat capacity, it can be written as: the temperature after inflating is. The mass entering container then is. For a particular case, if the container is evacuated to P1 equals 0 and M1 is 0 before inflating. The temperature after inflating then is. This means that if the vacuum container is adiabatically inflated, the temperature of the gas after entering the container will increase to gamma 0 times the original. That is, fill the vacuum container with compressed air under adiabatic conditions. If the original compressed air temperature is 300 Kelvin, after the air enters the container, the temperature will reach 420 Kelvin. The reason why the temperature rises is because the pushing work at the time of inflating is transformed into the thermodynamic energy of the gas. Now let's talk about the slow inflating or the constant temperature inflating. If the gas is treated as ideal gas with a constant specific heat, then U2 equals U1. Therefore, from equation 899, we have heat transfer with the surroundings. Usually, we have this temperature relation. Therefore, we have negative Q. This means the container will release heat to its surroundings in the isothermal inflating process. The mass entering the container during the inflating process then is. Okay, that's all for this task. Thank you very much and see you next time.